When we come back from spring break, we have one more lesson. Now, the cool thing about that last lesson is the last lesson is not part of the Calculus AB curriculum this year. I'm still going to show it to you because it's a huge time-saving device, and you'll use it. Got it? Good. Could you pass one out to everybody? Thank you very much. But next year it will be part of the calculus curriculum, which you don't really care about. Today we're talking about work. A lot of people hate work, cuz.
Force times distance.
Excellent. Thank you, Max. We're done. All right, so force times distance is what we're going to use for a constant force. Okay. How much force you apply over how much distance, very simply put, and the output is what we call work. However, this is calculus, so we're going to look at what happens when the force varies over time, or it's what's called a variable force. Okay. So in other words, if I just start pushing on something, if I just start pushing Nikki here, and I apply a constant force, she's going to move with a certain amount of work. If I change the force, then we get this scenario, and we're going to take a calculus approach to that. And then, of course, you should become a Jedi Master. Because everybody wants to be a Jedi Master.
Is this good for 6.3 still or 6.4?
This is
7.5. I made 7.
7.5.
If we don't
I
have
understand.
lightsabers.
You like lost a whole
It
chapter
was
somewhere.
7 something.
I
and
understand.
said
Serena, do you have any lightsabers?
No. I'm not a huge Star Wars fan, to be honest.
Really?
No, it's just. As Max blurted out, work equals force times distance.
Oh.
Okay. We're going to look at a whole bunch of examples. In fact, I have 3 or 4 examples for you today. I don't remember how many are on the page. We're not going to do too much with constant force because that's just a multiplication problem. Okay, I have one for you. It looks like, oh, this is important. Most of the time in our calculations, we're going to use force as weight. Does everybody understand why weight is force?
Units with gravity, or units over gravity? No.
Whatever the units are, but it's the amount of gravity, the force is gravity acting on that, and that generates weight. So the difference between mass and weight, you all are good with that, right? Because you've all had physics? I'll just pretend you are and move on. Okay. Most simplest force problem you're ever going to look at. I have a 50-pound object, I push it 4 feet. What's the force?
200.
Sorry, what's the work?
200.
200, okay? There it is. Oh, there's a nice graphic. And look, you can all multiply 50 times 4 and get 200 foot-pounds. Those are our units there, foot-pounds. Which is a little weird. There's nothing exciting about that. Okay? It's just, that's it. That's constant force. We're going to look at something more interesting. What happens when the force changes over time? So first one is blah, 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 blah. Boom. Okay, now where does that come from? What we're going to do is we're going to take the object and or the situation and break it into a really tiny piece. Now sometimes that piece will be a sliver of water. Sometimes that piece will be, will be a chunk of an object that we're lifting, depending on the scenario. But we're going to split it into a small piece, and then we're going to use the integral as an accumulator, like we always do, to add up all that work. So we calculate the work on one sliver, use the integral to calculate all the, to accumulate all that work, and then we get the final work. Similar to the related rates problems, these are nastier to set up. The calculus usually isn't that bad. Okay, there's the force, that's our function, and then dx is our distance. How far are you moving that thing? And this will start to become a little bit more clear. That was proper English as we work through this. Okay, so Robert Hooke, there he is. In case you wondered what Robert Hooke looks like. Did some work with springs. You did springs in physics, right? Yeah. Okay, so you know this. Force equals kx. Yeah, spring constant times the distance the spring is stretched. So if you have a spring, when you start stretching the spring, it's easy, but then as you extend the spring further or stretch it further, you get more force, or it requires more force to stretch it. Right? Like if you have a slinky. You all know what a slinky is, right?
Yeah.
No. Do they?
Do you have it on the bag?
That would be
Good prize.
That'd be,
I don't think there's a slinky in
we're
there.
not doing.
That would have been great, wouldn't it?
There's
If I,
hesitation, you might as well check.
right. Well, no, I'm sure there's not a slinky. I had a slinky, I don't know what happened to it. All right, so let's look at an example there. There's some springs. 12-point force to use a stretch spring from its neutral length of 8 inches to 11 inches. How much work is done in stretching this spring from, oh, we got two parts here, from 8 to 13 or from 10 to 13? Okay. So, first things first, we need to find the spring constant. So f of x, capital F of x, because we're using that for force, is equal to k times x. Okay. And with springs, you commonly use this term called the natural length. That's the, if you just drop the spring on a counter, that's the natural length. Okay, so if we take it from its natural length to 11 inches, we're moving at a distance of 3, and we know that that requires 12 pounds of force, because that's given information in the original problem. Therefore, we know for this particular spring that k is equal to 4. Okay. Are we good on that? Similar to the Pert equations, we need to find the rate first. With springs, you need to find k first, which is the spring constant, and then you can take that and move on and solve a bunch of other problems. In fact, we're going to figure out what it takes to move it from 8 to 13 and from 10 to 13. Okay. If we consider 8 inches to be 0, then if we're going to go to 13, we're actually going to stretch it a distance of 5 units. Okay. Right? Okay. Now, the second part, we're going to go from 10 to 13. What is x? 2 to 5 again, right? Okay. So we get that. When you're dealing with springs, the force that you're using is Hooke's law, which is kx. The distance that we move it is a little bit, dx. And we're going to figure out what happens when you stretch it from the natural length of 8 inches to the distance of 13 inches, which is a total movement of 5 units. So think of it this way. If you take a little piece of that spring, there's a certain amount of force that acts on that little piece of spring. We want to look at little pieces of spring from 8 to 13 inches, the natural length up to the distance that we're extending it. And you can see, like I said, that's an easy integral. Okay, so take it through that, and we get 50 inch-pounds. Not bad. Second part, the only thing we're changing for the second part is we're changing x to 2 to 5 instead of 0 to 5, and redoing the calculation, and we get 42 inch-pounds. Okay, so springs are really pretty straightforward if you can find that k value initially. Okay, we good? All right, let's look at this guy. A cable which is 50 feet long weighs 150 pounds. It hangs over the edge of a building and is used to lift an 800-pound beam. How much work is done lifting the beam 20 feet? Okay, so first things first, what doesn't change in the problem?
Weight.
Of?
The beam and the cable.
No, the cable weight will change. Why will the cable, oh, so hold on, let's do the first part. Yeah, the beam is constant. 800 pounds, never changes throughout the problem. Why does the cable weight change?
Says you won't add more weight. As you add more weight, then,
Well, it's the other way around. As you take weight away, because we're pulling it up.
oh,
If we were letting it down, then we'd add more weight. As we pull it up, we reduce weight. Is that what you were going to say? Yeah. So the cable weighs a certain amount, but as we start to pull it up, not all of it is hanging over the edge. So that this becomes a variable force problem. Okay, so there's our scenario. You can set this up a couple different ways. I chose to call the distance from the pulley x. That means the rest of the distance is 50 minus x. Okay, because the whole thing. My picture isn't 100% accurate, but the stuff that we pull in would be X. The remaining amount is 50 minus X. That stays constant. The weight of the beam never changes. Okay, we talked about that
So that
already.
whole thing is 50 feet long, like the.
Correct.
Okay.
The starting amount of cable is 50 feet long. So you'll see the calculation. I took 150 pounds of cable, divided it by the length of the cable to figure out that that cable weighs 3 pounds per foot. And we can continue to do that calculation and say, well, how much is it per inch? How much is it per eighth of it? You know, and keep getting smaller and smaller. But that will work for us because we're going to deal with feet in the problem.
Wait, what'd you do again?
150 divided by 50. 150, 50 feet of rope.
Oh, because it's 50.
Yep. And like I said, the 800-pound weight stays the same. So we get this. This is the weight of the scenario that we're dealing with. This never changes. We initially start with 150 pounds of rope, but if I pull, or cable, if I pull in X feet of cable, then I'm going to reduce the weight by a certain amount. That's why we had to calculate how much weight. Does that formula make sense? Yes or no?
Yes.
Is everybody confused?
So 3x is how much rope you're pulling in?
X is how much cable I'm pulling in. 3 times X is the weight of that cable that I'm pulling in.
Okay.
Wait, can you just explain it one more time?
If I pull in 2 feet of cable,
Yeah.
I now have that 2 feet of cable weighs 6 pounds.
Uh-huh.
So I have 6 pounds less than what I started with, which was 150.
Got it.
Okay. That's our weight. How much are we gonna move that thing? We're gonna move it just a little bit. But then what we're gonna do is calculate what happens if I move it a whole bunch of little bits. So this is weight, which is our force. Our distance is dx, and we want to integrate it from 0 to 20. So that's kind of a weird concept here. We're calculating the weight of the object, also known as the force, times the distance we're moving it. So you might want to say, well, I'm moving it 20 feet. No, we're moving that little piece just a little bit. And then we use the integral to accumulate all those forces to move all those little distances. And again, not a bad integral to solve, correct? Yeah, good. How would you solve that integral?
800 plus 150.
Say again?
Well, first you have to add 800 plus
950.
150.
And then integrate.
Yeah,
What's the antiderivative of 950?
950x.
And what's the antiderivative of negative 3x?
3 halves x over, raised to
Raised to second power. Good. Plug in 20, plug in 0. There's our weight. There's our small distance. How many small distances do we want? We want small distances from 0 to 20. 18,400 foot-pounds. Now, I would say to you, does that answer make any sense? But I have no idea what a foot-pound is. I have no idea whether that's right or wrong. I'm going to trust it. I wouldn't know if that's right or wrong. Well, I would if I got something absurd like a negative answer, or a, 4 gabillion would probably not be a correct answer. Okay. What does it weigh? How far are we moving it? Done. This is, I'll use the word they, this is their favorite type of work problem, and that is filling and emptying tanks. Okay. And we saw something similar to this when we were doing related rate stuff. Here's my inverted cone tank, because there's a lot of those laying around. The concept is we're going to figure out what it takes, or how much work it takes to move one little sliver of water out of the tank. And then I'm going to integrate it over the whole distance. Does that make sense? In other words, I have a little sliver of water right here. I'm going to figure out the work to get that out of the tank, and then I'm going to integrate all the little slivers of water inside the tank. We do need a little bit of a chemistry lesson here in density. You know density, right? What is density?
The weight per volume.
Correct. Weight per volume. So we're going to have to calculate the weight of that sliver of water. And in order to calculate the weight of that sliver of water, you have to know that the density of water is 62.4 pounds per cubic foot. You're not going to need to memorize that. And in fact, most of the time in a problem, they won't tell you what it is. It'll be some mystery fluid that has a density of blah, blah, blah. So it might be motor oil, it might be water, it might be Kool-Aid, who knows? But they will tell you the density. Okay. So what's the, and let me show you the rest of this. The cone has a radius of 4, it has a height of 20, and I randomly picked a sliver of water X units away from the top. This is how I decided to set it up. You could set it up differently. You could measure the distance from the bottom. I think this works a little bit better. If that sliver of water is X units away from the top, then the rest of it is 20 minus X because the whole distance is 20. Okay, so far. Question number 1, what's the volume of that sliver of water? What shape is that sliver of water? Hmm?
Circle.
Nope,
Is it
it's a disc, correct. How thick is that disc?
DX?
dx.
Yeah.
So again, what's the volume of that disc or that sliver of water?
The area times dx.
Good. The area times dx. So pi r squared times dx. Does that make sense? Okay, normally if you're calculating the volume of a cylinder, you would do base times height or pi r squared times h. But we want a really skinny sliver, so h is dx. That's the volume. But we don't want the volume, we want the weight. So you have to take the volume and multiply it by the density. That will give you the weight of that sliver of water. You with me? Okay, good. Yeah, we talked about that. Okay, great. And here we go. Pi r squared dx times 62.4. That's the weight of that sliver of water. And if you look at the picture, how far am I moving that sliver of water? X, right. Because once it gets above X, it's out of the tank and we're done with it. So we get that. This first stuff, pi r squared dx 62.4, is the weight of that sliver of water. We're moving that sliver of water X units to get it out over the top of the tank. So that's our weight, that's our work to move that sliver. Then we use the integral to take slivers of water from 0 to 20. We're emptying the entire tank. If we were only emptying the top half of the tank, then we have different limits of integration. But here we're emptying the entire tank.
Why is there an X on the other?
Because that's how far we're moving the sliver of water.
After 62.4?
Yeah.
Oh, yeah.
Okay. Notice I moved the 62.4 and the pi out in front because those are constants. I don't want to worry about them. Put them out in front and then deal with that little guy. What's wrong with that integral? Two variables. Can we get rid of one of them? Well, I hope so, or we're dead in the water. Which one?
Get rid of.
Which one do I want to get rid of, X or R?
Well, you can plug in 4 from R.
Why do I want to get rid of R?
Because d dx.
Yeah, I've got the dx, which says my variable is X. How do I get rid of the R squared?
Do you like a portion?
Yeah. Similar triangles, which are here. Okay. So 20 minus X over R is equal to 20 over 4. Do the math, blah, blah, blah. R is equal to that mess, 4 minus 1/5 X. This one ramps up a little bit. Because now we need to take that value of R, plug it back into the original integral, square it, mul- and multiply it out. Just for giggles, what's 4 minus 1/5 x quantity squared?
150 x and 125 x squared.
Do it in order.
Okay, 16.
16 minus
16
8/5 x plus 1/25 x squared. And all of that times x, which I have there. And then I made kind of a big leap of faith there. I didn't even multiply it out. Fn int times 62.4. And in this case, I chose to leave the pi in the answer there. You didn't have to. You could multiply it by 62.4 pi. But I didn't want to spend the time doing the antiderivative when I just want to get to the problem itself. Does that problem make sense? How much work is required to move one sliver of water? Once you get that work, then you integrate to add up the work for all of those slivers of water that go from 0 up to 20. You got one more on there? What are we doing next? Oh, leaky bucket. I love the leaky bucket. Let's stop and not do the leaky bucket. We'll do the leaky bucket tomorrow. Because that gets a little bit more complicated. And I want to